Hello and welcome to this short video that explains the basic functionality of SciScan 1.0 Resonance Scanner version. My name is Bruno Pichler and I'm the lead author of SciScan. This video assumes that you have already installed all the prerequisites for SciScan and configured the system to work with your hardware. If you haven't installed the prerequisites yet, please go to our knowledge base online at sciscan.scientifica.uk.com and follow the instructions there to install all the prerequisites. Alternatively, get in touch with your Scientifica representative and they will be able to assist you with installing all that. We also have a few other interesting videos online which will show you how to unzip the downloaded file and how to then confirm your INI settings. None of that will be covered here in this video, so please refer to the other videos. And for this video, we'll start at the point where you've already got your LabVIEW project open, and it is important that you start SciScan from within the project because it needs to have all the references right for all the other VIs that it draws upon. So if you're in the SciScan project, navigate to SciScan 1.0 Resonant.vi and up comes the SciScan user interface. As is typical in LabVIEW, you will need to press the Run button for this program to actually execute. So you can see once you hit the Run button, it starts by loading all the modules. These modules will be the ones that you've previously configured in your INI file. And again, please refer to the other videos if you haven't configured the INI file. It is important that the INI file has all the correct modules in there to work with your specific hardware. So I'm just going to go ahead here and set my PMT gain. I'm going to set that to a relatively low value here because we're just imaging pollen grains. For real tissue, you would probably want that to be more in the range between 750 and 850. You can see that we also have a laser power control here. This has already been calibrated in our system, and the calibration procedure is also explained online in the knowledge base. In addition to the laser power control and the PMT control, we've got a number of advanced controls down here which we'll mention a little bit later. But then we've got this main section here where you control all your 2D frame scan settings. We've got the general settings like route path and experiment name, and also the control for how many channels to save and whether they should be inverted or not. We've got the Z-Stack tab, we will talk about that a little later. And we also have a piezo tab here where you configure fast volume scans. Now in this section up here you've got a control over your XYZ stage and a few settings for that XYZ stage. In this area here you've got a notebook where you can record timestamps, type notes in, those will be saved with your experiments. This can be quite useful when anything unusual happens during an experiment, and you can type in there when you maybe top up the anesthesia or something like that. It will automatically, every time you record, save all the contents of this notebook as a text file with your image files. Obviously, you can also clear the contents just by clicking here. The section over here provides useful information about grayscale values such as min, max, and also the histogram will be displayed here. You'll see that later. And you've got these different channels here, histogram for channel 2, channel 3, channel 4, channel 1. You can also change a number of display parameters here, like the display palette. And then you can specify if you want to display an average image, whether it should be a group average or a moving average. And up here is your main imaging area where you have the channels 1, 2, 3, and 4. You also have an overlay panel here and a region of interest panel. We will talk about that a little bit later. Sometimes you may not want all of those panels open at the same time, so you can just tick that little pin button there and it'll move those tabs out of the way. You can also move them all out of the way by close settings, and if you press that again, it will just open them all again. Now we can start imaging. Just press focus here, and after a few seconds the image will pop up. And you can see here that the calibration of our laser power is such that I need to turn it all the way up to about 50 or so to actually see some pollen grains here. Now I'm just going to set my average type here to a moving average, and then I'm going to zoom in to this pollen grain here, and you can see there are these interlaced lines at the edges. These comb artifacts that are typical of resonance scanners, and they are due to the bidirectional scanning of the resonance scanner. Now we can correct for those by changing the value here for our start delay. There's a number of ways to adjust that start delay, either by clicking those up and down arrows here, or alternatively you can just type a number here in that field, and whenever you change that value it will briefly stop focusing, closes the shutter, and then restarts again, and you see it's now better aligned than before. Now I'm just going to show you a third way of using this, that I'm going to move it back to a incorrect start delay, so now you can see those comb artifacts very clearly again. And I'm just going to hit that green button, and the software will try to automatically determine the best start delay value. And you see it's now adjusted it correctly by itself. So that start delay value is a rather important concept here, so I want to talk about that a little bit more. If you change your scan resolution, for example, to a 1024 x 512 image, you'll sometimes find that, now when you reset the zoom here, you'll find that of the forward and backward line are not, there's comb artifacts, but the forward and backward line are really very far spaced apart. And in cases like this, you will first have to correct the start delay manually before using the auto calibrate button. So I'm going to do that here now. I'm going to move that around 1300 somewhere, and then you can see that the forward and backward line are now much better aligned. Now I'm going to hit the autocorrect button, and it will now remind me that I will need an average image here. So I'm just going to set that average type here from none to group average. And then you can see when I hit the autocorrect button, it will start calibrating and will give me a much better aligned image. It's not perfect yet, so I'm going to hit that again. And now when I zoom in, I find that there's probably still a little bit of improvement, so I'm going to try that again. And now my alignment is perfect. The autocorrect function works on the image content. So if you've got an image that is very noisy with very little features in the image, it may not always work perfectly. Another little thing that I want to point out here is that these white lines up here, they are the flyback of the Y mirror, meaning that all the data is being written into the image. There's no data discarded, even if it's collected during the flyback of the Y mirror. For analysis purposes, you can safely ignore those lines, but the reason to keep them in the image here is that it makes it easier to reconstruct the exact timing for each of the lines in the image. If we go back now to a 512 by 512 image, you will again see those double images where the forward line and the backward line are very poorly aligned, and that leads to this sort of double image. You also see that your frame rate has now halved, which means that your start delay is way off, and as soon as you bring that start delay back to a correct value, the frame rate also goes back to its original 30 Hz for a 512 by 512 image. And now we can use that autocorrect button again to calibrate. And now if we zoom in, you'll find that we're still not quite perfectly aligned. There's still some comb artifacts here, so we just hit that button again, and that should do the trick. The next thing we're going to talk about is how to move the stage around. So for that, you'll just reset the zoom first. And you've got these buttons here that will move the stage in the different directions. You can change the step size here. I'll just switch off the averaging here. Also for the stage motion, you can always reverse the direction here, depending on which one feels more intuitive to you. Now before we start recording, we should navigate to the general settings and make sure that we have the correct file paths and everything. Note that the file format is always going to be 16-bit raw. So once we're happy with the root path and the experiment name, we can move back to the 2D frame tab, check that the number of frames to acquire is correctly specified, and then we just hit record and run the recording. This automatically creates an entry in the notebook for a recording start, including a timestamp. And then when the recording ends, you'll get a recording end. So whatever you would have typed in between for a long recording would be bracketed by this recording start and recording end, and that gets saved with the images. So let's just have a quick look at what that looks like in the file structure. So inside your root path, you'll have a date stamped folder, and inside there you'll have a folder with date and timestamp and experiment name. And in here you'll find the INI file, which contains all the metadata that was used to record this file. So this can be very useful for data analysis. So all this metadata can be easily parsed in MATLAB or in Python, for example, for your analysis. We also have our notebook file here. It doesn't contain any notes, it just contains this recording start and end, but the file is there. We also have the raw file in here that contains the raw image data in 16-bit format. We have an image.j macro and a Windows batch file. If you click on that Windows batch file, it will automatically bring up image.j and load the whole recording. In this example, we recorded 2 channels, but there wasn't actually anything connected to channel 2, so the channel 2 image will be just gray noise here, basically. To separate those 2 channels in image.j, you can use a plugin called the interleave. You just need to specify the number of channels that you recorded, and image.j will automatically do that for you. And obviously you can do that in your own analysis routines, whether it be written in MATLAB or Python or anything else. So you see the noise channel, and this is your data channel, so that would be channel 1 and channel 2. In the next section, I'm going to talk a little bit about the Z-stack and how to configure those Z-stacks. So for that, I'm just going to move to a plane just above the pollen grains that we see here. Then I'm going to move to the Z-stack tab. Now before I add my first plane here, I'm going to set all my XYZ positions to 0. That changes the relative position, but the position that's being recorded in the table here is still the absolute positions. So just bear that in mind, that these are the actual absolute controller positions, not the relative positions. Now, while I'm stepping through the different planes that I want to later record, I might find that I need to adjust the laser power a little bit. So now if I add that value, you can see that the new laser power value gets added as well. And again, I'm changing that back to a different value, add another position. You see that all the XYZ positions and the laser power is being recorded. Once I've configured the laser power for various planes within my volume, I can then go on and configure the number of frames that I want to record per plane, and maybe also change the Z spacing in between, and it will then automatically calculate the correct number of frames, of total frames to be recorded. Then I just need to move back to my start plane and hit the Start Z-stack button. Maybe I'll clear the notebook beforehand. And now I'm ready to go. I hit the Start button, and it will automatically step in Z through that volume. You can see the pollen grains coming into focus on the left-hand side. And you can also see how the relative positions are moving, and how also the laser power changes while we're moving through that volume. And that's all interpolated values from the table that you see in the bottom right. Once that is done, we can then move over to our file structure and just see what we've recorded. Again, date stamped folder, date and time stamped folder with experiment name. And then in here, just double click the batch file. It comes up in ImageJ. I'm going to use my deinterleave. Got my 2 channels here. And now if I run through that, you can see how the pollen grains come into focus and run through that whole Z stack. I'm going to speed up the video here while I'm bringing those pollen grains now back in focus after our Z stack. You might have already noticed that in this drop-down menu we also have an arbitrary Y pixel option. You can choose any number larger than 60 to type in here and record much faster frame rates that way. Obviously this sacrifices the number of lines you can record, but you can see here that very high frame rates are possible with this arbitrary Y mode. Let's change back to 512 by 512 geometry. And the last thing I want to show you here is the region of interest analysis. This allows you to monitor the average grayscale value in a given region of interest. Plot it here in this graph. So you've got a number of right-click options here, so you can clear that chart. You can also change the scaling here simply by clicking in there and typing a different number. That can be very useful to give you a first indication of whether you have activity, for example calcium signals, in your regions of interest. Now this concludes this short introductory video. Please don't hesitate to get in touch if you have any further questions. Thank you very much for your attention.